Thank you. I'm Rupak, and I'll be talking about our recent progress on scrape-off layer turbulence using Jekyll, which uses a discontinuous Galerkin method with full F gyrokinetics and further with electromagnetic capabilities. So what we are simulating? We are simulating the scrape-off layer turbulence of a tokamak in the all bad curvature region around the outboard midplane. So here you can see this shaded region in green, this part. So, however, we do not have shear in our code currently for these runs. So we straighten the field lines like this, and in the simulation domain at a fixed toroidal angle look like this. So even though this looks elongated in 2D, actually these are helical field lines like this. And this is a 3x simulation in full 3 spatial dimensions. That's why I mentioned how are we simulating. These are 3x 2v gyrokinetic equations on magnetic field line following coordinates. What are included? We have full distribution function to capture turbulence better. It has electromagnetic capabilities so that we are not running into issues with ampere cancellation. Further details you can see in Noah's JPP paper. We are using discontinuous Galerkin algorithm for better accuracy. And we are following helical magnetic field line geometry. I'm using this cartoon to indicate helical. And for the Leonard-Bernstein collision operators with cross-species collisions, so that electrons can collide with electrons itself and ions and vice versa. We have deuterium mass ratio, realistic mass ratios, and what are not included yet is our X points, neutrals. However, regarding neutrals, we have heard the immediate previous talk by Tess Bernard. So we have implemented neutrals, but for this specific current runs that the results that I'm showing here, neutrals are not included. Similarly, on Monday morning, you had heard Noah's talk on shear in the magnetic field that has been included now. But for this specific runs, the shears, there are no shear. And similarly, the space-time dependent collision operator. So these are not there. We have the boundary conditions, these. And further details about the DG and discontinuous Galerkin algorithm and magnetic field line following geometry regarding tokamak SOL modeling, you can find in the Jekyll website in this section by the presentations of Noah. So we have done this simulation for experimental parameters which are close to ASDEX short number this and this. The further details of the experimental parameters, etc., you can find in Daniel's paper, 2017 nuclear fusion paper. This one. The experimental inputs are mostly known for the ASDEX, these things. And for these specific shots, we are using the power in the SOL region as 0.47 megawatt, which we will be calling as low case, and 0.8 megawatt, which we'll be calling as the high case in future slides. Numerical input parameters. So we are taking the ion density, which is 7 into 10 to the 18 per meter cube. We'll be calling this case as low density, and this case, the other 2 into 10 to the 19 is as the high density case. So these numbers we have taken from the experimental, from this experimental paper, but these are just the initial conditions. So all the profiles, this initial ion and electron temperature profiles and everything, this is just to start the simulation. They evolve self-consistently and they take some other values. The SOL plasma parameters are these. You can see for 2 different cases. For this plot, this is the plot that will be coming back in the next, coming again in the next slide. So we have to understand this. This is the radial direction, radially outward direction. This is the binormal direction, which is the normal to the radial as well as the helical, the magnetic field direction. Even though it looks like a straight line, it is actually a helical direction, like goes like this. And this is the separatrix at some plane. This is at around 2.147 meter, and as you can see, this is the ion density. Ion density for the ASDEX like parameters at some steady state, and you can see the blobs that are coming out in this direction. So this part is the SOL region or the scrape-off layer region of the tokamak, and the blobs are coming out like this. So here you can see the density blobs for of the order of 1 millisecond in real time, how they're coming out and filling up the SOL region, causing turbulence in this part. Also, you can see the field lines are moving because of the plasma turbulence. So to capture these things better, I'll go to the next slide. Here I've just reduced the transparency, and you can see, remember these magnetic field lines are actually the helical magnetic field lines that go like this in the tokamak. But they are vibrating due to plasma turbulence. So this vibration of the magnetic field lines, they're happening because of the plasma turbulence in the system. And these are vibrating in 3D. Now, if we go to the next slide, this one, the time evolution of the ion density isosurfaces. So this is basically this is being plotted the ion density, and this is the isosurfaces of some two different values at two different transparency, these two values, and you can see that they form the blobs, and you can also watch the blobs are following the magnetic field lines. The magnetic field lines are extended in this direction like this, even though this is helical. And so here you can see the blobs are elongated along the magnetic field line. That's why I see the benefit of using field line following coordinates. Density blobs are isosurface elongated along magnetic field line direction, the z-axis. This is z-axis. This helps in reduction of the computational cost. These blobs actually shear off and propagate radially outward. So this is the radially outward direction, this one. And this enhances the turbulence in the SOL region, scrape-off layer region, and this is how it helps in reducing the diverter heat load as we make more turbulence. So these blobs, you can see in the Daniel's paper in PRL 2015, the blobs are actually elongated like this along. So this is the magnetic field, and the blobs are elongated. So this is the magnetic field line direction where the blobs are elongated. Yes. If I compare the time averaged, the time average has been taken over 0.5 millisecond. Time averaged electron and ion densities. These are the parameters, and electron and ion temperatures. These are the plots, and you can see the profiles of the numbers, and the profiles are sort of close to the experiments, not exactly one-on-one, but the profiles match. And also the electron and ion temperature, you can see that even though we start from the same temperature for electrons and ions for both the different cases, however, as we see in the experiments, the ion temperature becomes almost double, or in fact more than double than the electron temperature. So this is a good signature that we are capturing. We are close to the experiments. Statistics of turbulence, you can see the high density runs, which I mentioned earlier. So these are actually the high density, high power runs. They have more density fluctuation, more skewness in the density, and more kurtosis in the density. In fact, in the potential also, they have higher skewness and kurtosis in the fluxes. So overall, we call that the runs with higher density. They're more intermittent, and they have the high density case has more radial particle flux also. You can see, and if I calculate the parallel ion heat flux in the diverter plate, we also see that the high density runs have more heat flux. It is throwing in the diverter plate compared to the low density run, the blue one. So in summary, the Jekyll code can now capture, using its full F gyrokinetic electromagnetic capabilities, including it can capture the blobby features that are happening in the SOL region, SOL plasma turbulence, for the realistic ASDEX like parameters. And we see the ion temperatures are almost double the electron temperatures. However, more realistic features, for example, the shear in magnetic field, as I mentioned earlier in Noah's talk, and neutrals, as you heard in last talk by Tess Bernard, they are being incorporated in Jekyll soon for a better comparison with experiments. I acknowledge Jekyll team and Gregor, Thomas, Vladimir, Dominic, Andreas, and Frank from IPP. And if you're interested, you can go back to Monday's morning's Noah's invited talk on mappage turbulence for NSTX like semi parameters. Immediate previous talk that had happened by Tess on neutral transport, and the last talk in this session by Mana, he'll be talking about the general overview of Jekyll.